Greetings, Mr. Perry here, as we continue with the fourth segment in this unit, the unit entitled Forces and the Universe. We covered in previous editions potential and kinetic energy, thermal energy, and today we're going to cover Newton's three laws. So let's move forward. We'll first take a look at Newton's first law of motion, called inertia. An object will not change its motion unless acted on by an unbalanced force. If it is at rest, it will stay at rest. If it's in motion, it will remain at the same velocity. Objects with greater mass have greater inertia, and it takes more force to change their motion. Let's watch.
Welcome to Newton's first law of motion, the law of inertia. Sir Isaac Newton was an English mathematician, astronomer, physicist, and philosopher. He lived during the last days of the Renaissance period, and his work in physics laid the foundation for the modern age. His book, Mathematical Principles of Natural Philosophy, first published in 1687, laid the foundation for classical mechanics. In the book, Newton outlined his understanding of motion. His understanding became the driving force for how all scientists understand the physical universe today. For the past 300 years, Newton's helped scientists understand how comets move through the night sky, how waves and tides collide with the shore, and how planets move through the universe. Even today, if you're trying to explain how forces affect any object, including an apple falling from a tree, it lying on the ground, or that same apple being thrown across the orchard, you're going to want to use Newton's laws. His first law of motion sets the stage for how everything in the universe is related. An object at rest stays at rest. An object in motion stays in motion at a constant speed in a straight line unless acted on by an external unbalanced force. Newton's first law is all about inertia. It describes why an object has the tendency to keep doing what it's doing. Throughout the universe, moving objects like to keep moving, and resting objects like to rest. Basically, if you want to change an object's inertia, you need to use force. An object at rest stays at rest. The fallen apple stays on the ground. Newton's first law explains that the apple will keep doing what it's doing. Every object resists a change in its state of motion. The apple stays where it is. That is, until your little brother picks up the apple and throws it across the orchard. Then we're on to the second part of Newton's first law. An object at rest stays at rest unless an external unbalanced force acts on it. I'm not saying your little brother is unbalanced, but he's using an external unbalanced force to launch the apple across the orchard. He's using the strength in his arm to pick up and throw the apple, which is greater than the resting force currently acting upon the apple. In this case, the apple's ability to remain at rest has been overpowered by an external and unbalanced force. It's now flying across the orchard. Next, we get to an object in motion stays in motion at constant speed in a straight line unless an external unbalanced force acts on it. The apple now continues in a straight line across the orchard until it falls back to the earth after hitting a tree, hitting a fence, or encountering enough resistance in the air to stop its motion. Any of these act as another external unbalanced force that changes the apple's state of motion again and causes it to return to a state of rest. Unless, of course, your little brother runs after the apple, picks it up, and starts the process all over again. In summary, Newton's first law states, an object at rest stays at rest. An object in motion stays in motion at a constant speed in a straight line unless acted on by an external unbalanced force. That apple could be anywhere by the time you're ready to take him home. Thanks, Newton. Newton's first law of motion, the law of inertia.
Let's take a look at forces. Some examples of forces and how they work. Friction, a force that opposes motion. Three kinds of friction are sliding, rolling, and fluid friction. In our picture to the left, we see a box wants to move to the right there in that direction shown. And we also see friction, and friction is a force that acts in an opposite direction to movement. And to the right, we see the direction of motion of the lawnmower is to the left, while the force of friction, which might come from the grass he's cutting, moving in the opposite direction. Newton's second law of motion. The greater the mass of an object, the more force it will take to accelerate or increase the speed of that object. The more force, the more acceleration. So we have a formula, F equals m times a, or force equals mass times acceleration. Here's more.
Sir Isaac Newton. He came up with 3 laws of motion. We've talked about some of these before in previous episodes, and we're going to talk about his second law of motion. Now, his second law of motion states that the strength of a force is equal to the amount of mass involved multiplied by any acceleration applied to it. That sounds a little complicated, but I have a simple demonstration to show you how this works. I have 2 objects. One is red and one is yellow, and that's neither here nor there, but this one is heavier, and you're gonna have to take my word for it. I've got something inside the red ball, which does make it a bit heavier, and there's nothing inside the yellow ball. So I have 2 different masses, a heavier one and a lighter one. And I draw your attention to our high-powered air cannons, which I have here on the stage. Now, what I'm gonna do is I'm gonna try and move these, accelerate these objects across the stage, using exactly the same amount of force. So I'm gonna put one of our objects, the heavier one, here, and our lighter object here. The force is going to be exactly the same behind each object. So I'd ask you, which one do you think would go faster and farther? Again, the force is the same, but our objects have different masses. If we look at that second law of motion, it says the strength of a force is equal to the amount of mass involved multiplied by the acceleration. I don't want to give anything away, but let's actually try this. Now, I've done something a little risky here, which is I'm pointing them at Parnelli, who delivers our programs here, has graciously accepted the job of tester for this. I've loaded him up, and we're going to fire these directly at Parnelli, and he's going to see which one is going to travel faster and farther. You okay with this? You're good? Good, because your contract says you're allowed to do this. So we're going to arm our system. We're going to put in some air pressure, so there's enough to, that should be more than enough. And we're going to do a quick countdown and fire these at our brave volunteer and see which one is going to travel faster and farther. All right, we're going to go 3, 2, 1, and could you tell which one was going faster and farther?
I had my eyes closed.
I did notice that you had your eyes closed, but I can tell you without a doubt the yellow one, the lighter one, was going faster and farther. So, what did we have? The yellow one. The yellow one went faster and farther than the red one because, of course, it's lighter. It takes less force to move something that's lighter. Now, not only do we see this in rockets, you want to have a nice light rocket to go into space, you actually see this in everyday life. With the price of gas going up, you'll notice people are trading in their heavy trucks for lighter cars because it takes less force to move that lighter object. So again, something that we're going to be seeing a lot more of. If that price of fuel keeps increasing, we want to try and find a really efficient way of moving ourselves around. For the Express here at the H.R. MacMillan Space Center, I'm Cam Cronin. Thanks again, Parnelli.
Newton's second law of motion. Some examples of Newton's second law include, number 1, we have riding your bicycle. Your bicycle is the mass, and your leg muscles pushing on the pedals of your bicycle is the force. The more force you exert on the bike pedals, the faster the bike will go. Number 2, it is easier to push an empty shopping cart than a full one, because the full shopping cart has more mass than the empty one. Number 3, we have 2 planets, orbiting a star and are equally distant from the star. Each planet will have different accelerations in their orbit speed depending on each planet's mass and the forces exerted on them by the other planet and the star they orbit. Newton's third law of motion. Newton's third law: for every force or action, there is an equal and opposite reaction or force. Here's some examples. Rowing a boat, the boat paddle pushes water behind the paddle to move the boat forward. Walking, the balls of your feet push against the surface of the floor, and the floor pushes up against your feet. Rockets, the rocket fuel is propelled downward and out of the rocket while the rocket is pushed upward. Check this out.
Welcome to the International Space Station. I'm NASA astronaut Mark Vande Hei. Today, we're going to talk about Newton's third law. How do you think it will hold up in microgravity?
For every action, there is an equal and opposite reaction. This means that in every interaction between two objects, there are a pair of opposite forces acting on each object at the same time. A force pair. You can see that there are many examples on Earth. In space, thrusters expel one way and the vehicle is steered in the opposite way.
Hello again. More basketball stunts that I can't do on the ground, at least not while getting this much hang time. All right, back to serious business. Got a basketball right here. It's going to be object 1. I'm the second object. If object 2, myself, applies a force to object 1, then that same force will be applied according to Newton's third law by object 1 onto object 2. However, there's a big disparity in the mass. Object 1 is a very light mass object. Object 2, myself, is a larger mass object. So I'm going to try to make myself about the same shape as this ball. See how that works for us. And I'm going to apply that force. You saw that force applied to the ball made it accelerate quite a bit. It really didn't accelerate me much at all. Newton's third law again, but this time we're going to use two similarly massed objects. Joe and I have about the same mass, so Joe, get into a ball. I'll do the same. I'm going to face you this way so that I don't throw you into something you can't see. Now I'm going to get into a ball behind Joe, and I'm going to apply a force to him. Notice that when I applied a force to Joe, it accelerated Joe away from me, but I got accelerated away from him as well, because the force applied to Joe ended up being the same force that was applied to me. Now you've seen Newton's third law in space. Now test it out on Earth. See you next time.
How do Newton's first, second, and third laws apply to cars? Well, Newton's first law, inertia, an object will not change its motion unless acted on by an unbalanced force. Car will remain at rest, or inertia, unless it is acted upon by a force. And the force, gas, is fossil fuel energy that creates a push, a small explosion in the engine that moves the car. Once again, we have our formula: force equals mass times acceleration. Newton's second law: the greater the mass of an object, the more force it will take to accelerate the object. If the same amount of force is used to move a truck and a car up a hill, the car will move faster than the truck because it has less mass to move. Let's watch.
In this video, we're going to learn about and practice applying Newton's second law in calculations, relating force, mass, and acceleration. You have just thrown a ball, and it's travelling upwards, neglecting air resistance. What force or forces are acting on the ball? A. The upward force from your hand. B. The downward force of gravity. Or C. Both of these. The answer is just the downward force of gravity, which gradually slows the ball, stops it, then brings it back down, making it fall faster and faster. The unbalanced force here causes the ball to change its velocity. Now look at this ball thrown sideways, but with elastic attached. The force on the ball must be towards the hand, caused by the piece of elastic, which slows it down and then brings it back to the hand. This is just like the ball thrown upwards, except that it's the force from a piece of elastic that slows the ball and then brings it back. What else could happen to an object when subjected to an unbalanced force? When forces are unbalanced, objects can speed up, slow down, like the thrown ball, but also change direction. Think of trying to change your direction on a muddy football field. Normally, you dig your boot into the ground to provide the force to change your direction. But in the mud, you just carry on in the same direction, and you call it a skid. The larger the mass of an object, the larger is the force needed to change the direction or its speed. Think of trying to push a car compared with a bicycle. Also, the faster you want something to get moving, the bigger the force needed. Think of pedaling a bike. The harder you push, the quicker you get going. The relationship between force, mass, and acceleration is known as Newton's second law of motion. It can be summarized in this equation. Resultant force equals mass times acceleration. When force is measured in newtons, mass is measured in kilograms, and acceleration is measured in meters per second. A spacecraft with a mass of 7,150 kilograms accelerated away from the International Space Station towards its re-entry point with an acceleration of 2 meters per second relative to the International Space Station. Calculate the resultant force on the spacecraft. Pause the video and work it out. How about this example? A car of a mass of 1,200 kilograms starts moving and accelerates on a racetrack. The car's engine produces a constant force of 3,400 newtons. A constant frictional force of 400 newtons acts on the car. Calculate the acceleration of the car. Pause the video while you work it out. Now calculate the force required to make an 800-gram toy car accelerate at 8.2 meters per second. Take care with the units. And the mass of an object accelerating at 0.8 meters per second when a resultant force of 200 newtons acts upon it. So why do you think you can throw a tennis ball much faster than a shot put? Because the force from your arm is the same, but the mass of the shot is much bigger, so its acceleration will be smaller.
If you liked the video, give it a thumbs up and don't forget to subscribe. Comment below if you have any questions. Why not check out our FuseSchool app as well? Until next time.
And Newton's third law: for every force or action, there is an equal and opposite reaction or force. For a car to move forward, its tires must grip and push the surface behind to move forward. Watch this.
Hello,
name is Bruce Yaney, and today I'd like to take a quick look at Newton's third law. Newton's third law tells us that if we apply a force in one direction, there's an equal force applied in the opposite direction by the object that we're pushing against. So it shouldn't be too hard to understand. If I have a scale, for me to use the scale properly, I apply a force on one side. There has to be something that I'm pushing against on the opposite side. For example, if I put this down on the table, I push down on the scale. The table underneath it is actually pushing up against the bottom of the scale, and that's why I'm able to get a reading. If I push down harder, the table resists that and it pushes up harder. And so I still have an equal amount of force going down and an equal amount of force going up. Whatever force I apply against the object is then pushed back with the same amount in the opposite direction. Whether I use this type of scale, which is compressing, or whether I use a spring scale where I'm actually stretching a spring, it doesn't matter. If I hold one end, I can't get a reading unless I apply a force in the opposite direction. So if I pull on this side, pull up, I have to pull down on this side for me to be able to get a force. So that's Newton's third law. For every force, there's an equal amount of force applied in the opposite direction. Newton's third law also talks about action-reaction. Now, sometimes Newton's third law can be obvious. The action and reaction of this balloon is fairly simple. I filled it with air, and if I were to release it, the air is going out in one direction, and the balloon goes in the opposite direction. Action and reaction. Sometimes the reaction's not so evident. For example, if I put a line in the floor here, and I want to jump, I actually had to push back against the earth. I'm trying to push the earth backwards for me to go forward. Now, even though I explain this to my students, sometimes they still don't quite believe that that's the case. So here's one more example that we can try, is if I take a skateboard and I put it on the floor. Now if I try that same jump again, this time the results will be, you would expect to be quite different. I try and jump forward, and I can't, because I'm not able to apply enough force backwards. I've had kids try this year after year after year, and I simply can't get over this line. They say jump up and then go forward. Well, you can't do that. You can't go forward unless you can apply that force backwards. There's a lot of examples that we can use for Newton's third law. One of my favorites is simply to use a car, like this, a little motorized car, and turn it on. The car goes forward because the tires are applying a force backward. He talks about action and reaction. Well, we can see the car going forward, but what we don't see is that it's actually trying to push the desk backwards. So a simple way to see that is to take some pencils, spread them out on the table a little bit, and if you take a piece of cardboard and put it on top of that, it moves very nicely, very easily. And so now if I put the car on top of this, I would then ask my students, what's going to happen? And some of them will tell me the car will go forward, some people will tell me the cardboard would go backward, and some people will tell me the car will go forward, the cardboard would go backward, so we're going to see some of both. So I guess the easiest thing to do is turn it on. That is Newton's third law. For an object to go forward, there has to be something that's being pushed backwards. I can just hold on to it and see the same thing. In this case, it's pushing the cardboard back, and I'm massive enough to keep the car from going forward. So anyway, there's my first example of Newton's third law. Stay tuned because I will be showing some other ones in some later series.
Newton's laws applied to car collisions. How could you design a car to be more safe now that you know Newton's laws? Well, let's watch these two videos and see if you got it all figured out. Let's go.
Newton's first law of inertia states that an object stays in motion with the same speed and direction unless acted on by an external force. Normally, a car and its occupants move around at the same speed, but when an external force is applied to the car, in this case by the crash test block, the occupants continue to move forward at the same speed until a force is applied to them. This resistance to a change in motion is called inertia, and it applies even when the velocity is zero. It's this property that enables people to do things like this. The china on the table stays pretty much at rest even when the tablecloth's pulled from under it. That's because there's not enough sideways frictional force to overcome the china's inertia and get it to move. Back to the crash test. Because they're not wearing seatbelts, inertia means the occupants of this car continue travelling forwards until the windscreen applies the force to stop them.
Let's look at the inertia here. You can see the vehicle coming forward, it's stopping, but the occupants carry on because there's nothing stopping them carry on. That's the basic Newton's law here. So you can see the occupants, because they're unrestrained, the driver has hit the steering wheel and the whole steering column is crushed around him. You can see he's partially ejected and would be severely injured. The poor passenger, even though he was in the back of the car, protected by the front seat, because he's not restrained, he goes through the front seat and he's gone through the windshield, and you can see his head still sticking out there.
Of course, in real life, you get a lot less time to regret not doing up your seatbelt. Newton's first law gives us the idea that in a car crash, things keep going until something stops them. First used in the 1950s, seatbelts provide an external force that counteracts the passenger's inertia, bringing them to a halt in a more controlled way. But they're just one of the ways car designers reduce the forces on the occupants in the event of a crash. And every car designer also needs to understand the principle behind Newton's second law of motion.
This car was traveling at a normal city driving speed when it struck a barrier. The slow-motion cameras filmed the collision so that a 1-second real event appears for about 21 seconds on the screen. This greatly slowed action enables you to observe how Newton's laws govern the collision. You can observe a dramatic example of Newton's third law. As the car strikes the barrier, its front end exerts a force on the wall. In turn, the barrier applies an equal magnitude but oppositely directed force to the front of the car. This reaction force causes the car to decelerate and eventually stop. Using Newton's second law, you can determine the force applied by the wall on the car. By measuring speeds at various times during the collision, you can calculate the automobile's acceleration. With this value and the mass of the car, you can determine the force on the car. Newton's first law is demonstrated by both the car and its occupants. When the front of the car collides with the wall, it stops quickly. However, parts of the automobile further back continue their previous motion for a short time. Their inertia causes them to continue moving forward until they are acted upon by an external force. The lap belts worn by these passengers quickly apply forces to keep them in their seats. However, their heads and shoulders do not immediately change velocity. They continue to move forward until the shoulder harness exerts a force on them. Then they stop abruptly.
Well, there you have it. Forces and the universe. We had 4 segments, and we covered potential and kinetic energy, Newton's laws 1, 2, and 3, and thermal energy. We have a lot of information, hopefully, that you can use, and if you missed any part, you can back any individual segment up and listen to it again. Till you do that, we'll say, May the force be with you. Let's hit it and quit it. Let's get it done.